Hi, welcome to this walkthrough of Edexcel A Level Mathematics Paper 31, that is Statistics of June 2019. This paper contains 5 questions and is set for 50 marks in total. Before we start, let us discuss some top tips on how to avoid some common pitfalls that make you lose marks. Even though questions on the large data sets in Edexcel A-level papers are just for 2 or 3 marks, students usually lose marks because they misquote the units that are used for rainfall, atmospheric pressure, wind speed, cloud coverage, etc. So please memorize these because it's quite easy to memorize them. Also, before you whip out the calculator to solve a question immediately after reading the question, please note to write the probability statement or the distribution model fully, such as binomial or normal distribution with the correct parameters or the equation for calculation. Then use the calculator. This will secure you method marks. Another very common pitfall is students forget to apply the continuity correction while they move from binomial to normal approximation. If you are one of the students who quite usually forget to do this, I will tell you a smart tip to remember how to avoid this pitfall. I used to advise my students that there are 3 things to remember while you do the normal approximation of a binomial situation. Calculate the median, calculate the variance using the n and the p values, and then do the continuity correction. This checklist will always help to identify if you have done what all things that you need to do. Okay, more top tips in the next walkthrough. Now let's get on with the questions. Question 1. 3 bags A, B and C contain 1 red marble and some green marbles. Bag A contains 1 red marble and 9 green marbles only. Bag B contains 1 red marble and 4 green marbles only. Bag C contains 1 red marble and 2 green marbles only. Sasha selects at random 1 marble from bag A. If he selects a red marble, he stops selecting. If the marble is green, he continues by selecting at random 1 marble from bag B. If he selects a red marble, he stops selecting. If the marble is green, he continues by selecting at random 1 marble from bag C. Draw a tree diagram to represent this information. Let's firstly show bag A, bag B and bag C. When he selects 1 marble from bag A, the probability of getting a red marble is 1 over 10 and probability of getting a green is 9 over 10. If he gets a red, he stops selecting. If he gets a green, then let's represent his further selection. Here, selecting a red has a probability of 1/5 and selecting a green is 4/5. Again, when he gets a green from bag B, he does one more selection. That selection from bag C has a probability of 1/3 for the red and 2/3 for the green. Part B. Find the probability that Sasha selects 3 green marbles. So probability of selecting a green, again a green, again a green will be equal to 9 over 10 times 4 over 5 times 2 over 3, that is equal to 72 over 150. Part C. Find the probability that Sasha selects at least 1 marble of each color. The first situation where he can get a green and a red is from bag B, because if you consider bag A, he's not going to get 2 marbles of different colors. So let's write, from bag B he will be getting, the probability of getting a red is 9 out of 10 times 1 out of 5 plus from bag C 9 out of 10 times 4 out of 5 times 1 out of 3, and that's going to be equal to 9 out of 50 add 36 out of 150 equaling 21 over 50. Part D. Given that Sasha selects a red marble, find the probability that he selects it from bag B. So this phrase given that actually means there is a conditional probability applying there. The formula for conditional probability goes like this. Probability of A given B is equal to probability of A intersection B divided by probability of B. In the context of this question, what this means is probability of getting a red from B out of probability of getting a red from all the 3 bags. That's going to be 9 out of 10 times 1 out of 5 upon getting a red from all of them. So 1 out of 10 from bag A, 9 out of 10 times 1 out of 5 from bag B, plus from bag C is going to be 9 out of 10 times 4 out of 5 times 1 out of 3, and that gives 9 out of 50 out of 1 out of 10, add 9 out of 50, add 36 out of 150, altogether it works out to 9 out of 26. Question 2. The partially completed box plot in figure 1 shows the distribution of daily mean air temperatures using the data from the large data set for Beijing in 2015. An outlier is defined as a value more than 1.5 times the IQR below Q1 or more than 1.5 times IQR above Q3. The 3 lowest air temperatures in the data set are 7.6 degrees centigrade, 8.1 degrees centigrade, and 9.1 degrees centigrade. The highest air temperature in the data set is 32.5 degrees centigrade. Complete the box plot in figure 1 showing clearly any outliers. So let's first find the IQR and then the outliers. The Q3 is 26.6 here, and this is 19.4. Therefore IQR is equal to Q3 minus Q1 equals 26.6 minus 19.4 equals 7.2. Therefore outliers should be Q1 minus 7.2 times 1.5, that's equal to 19.4, take away 10.8, and that gives us 8.6. The second one will be Q3 plus 7.2 times 1.5, that is equal to 26.6 plus 10.8, that gives us 37.4. This means any data point less than 8.6 will be an outlier and more than 37.4 will be an outlier. So 8.6, 37.4. So looking at these values, we know these two should be the outliers, and 32.5 will not be an outlier. So let's mark 7.6 here and 8.1 here. Therefore the lowest point will be 9.1, that's here, and we need to draw this connecting whisk to the box. The highest point will be 32.5, which will be somewhere here. That's it. So these two are the outliers. Maybe we can point this out. Fine. Part B. Using your knowledge of the large data set, suggest from which month the two outliers are likely to have come. The large data set is for the period. The large data set is drawn from the records for the period May to October. Since the two outliers are the lowest values of air temperature, so it must be the starting point of winter or the end point of the autumn. Therefore, it must be the October month. So let's write from October 2015. Part C. Using the data from the large data set, Simon produced the following summary statistics for the daily mean air temperature x degrees centigrade for Beijing in 2015, where n is equal to 184, sigma x is equal to 4153.6, and summary statistic SXX is equal to 4952.906. Show that to three significant figures, the standard deviation is 5.19 degrees centigrade. The formula for standard deviation from summary statistics goes like this. Sigma equals SXX division AN. Going by the numbers given in the question, this is 4952.906 upon 184. Putting this into the calculator, we get 5.188, which is equal to 5.19 degrees centigrade to three significant figures, which is what the question wants us to show. Part D. Simon decides to model the air temperatures with the random variable T follows normal distribution 22.6, 5.19 square. Using Simon's model, calculate the 10th to 90th interpercentile range. So air temperatures follow normal distribution with 22.6 as mu and 5.19 square as variance. So if we draw the normal distribution graph here, okay, this is the mean, which is 22.6. Standard deviation is 5.19. So we are looking at this point and this point. Let us call this as A and this as B. So this must be 10% and this is the top end 10%. So what we need to do now here is find the values of A and B and find the difference between them, and that will be the required interpercentile range. So let's now go to the inverse normal distribution calculator and put these values. So area, let's put 0.10, mean is 22.6, and standard deviation is 5.19, and below this is 15.9487. So this A value is 15.9487. Let's go back to the inverse distribution calculator once again and select above. That is 29.2513. 29.2513. Therefore, the 10th to 90th interpercentile range equals 29.2513, take away 15.9487, which gives us 13.3026, and underline it. Part E. Simon wants to model another variable from the large data set for Beijing using a normal distribution. State two variables from the large data set for Beijing that are not suitable to be modeled by a normal distribution. Give a reason for each answer. Here we need to remember the difference between temperature and other aspects of measures such as rainfall, wind speed, pressure, etc. Temperature can fit into a normal distribution format, but rainfall is heavily skewed towards zero, as most of the days there can be very low rainfall or zero rainfall and a few days of heavy rainfall. Similarly, air pressure also is not a symmetric measure. Hence, we can quote rainfall and air pressure as two variables that won't be suitable for normal distribution modeling. So we can write the two variables that are not suitable for normal distribution modeling are: 1. Rainfall with reason, okay, as there is zero rainfall for many days. And hence it is skewed towards 0, hence not suitable for normal distribution. Second, air pressure. We can write it is not symmetrical. About any mean value. Question 3. Barbara is investigating the relationship between average income, that is GDP per capita x US dollars, and average annual carbon dioxide emissions y tons for different countries. She takes a random sample of 24 countries and finds the product moment correlation coefficient between average annual CO2 emissions and average income to be 0.446. Stating your hypothesis clearly, test at 5% level of significance whether or not the product moment correlation coefficient for all countries is greater than 0. So this question is based on hypothesis testing based on product moment correlation coefficient. Testing whether the product moment correlation coefficient is greater than 0 is actually a test to see whether there is a positive correlation. So we will start with saying the null hypothesis that rho is equal to 0, which means there is no correlation, and therefore the alternate hypothesis will be rho is more than 0. Let us also list down all the other bits of information that we have. So we have been told that the R is 0.446, N, the number in the sample is 24, and then alpha is equal to 0.05. Let us now find the critical value for the table. The table shows N here. Under that you look for the sample size of 24, and here 0.05, which is the alpha value. Under that, when I go across, I see 0.3438. I'll tell you the best method of presentation for this PMCC related hypothesis testing questions. Put the R value here, 0.446, and put 0.3438, the critical value that we found out. Now, this means this is greater than that, right? Now, to check whether this is in the acceptance or rejection region, I would suggest you draw this sort of number line and say 0.3438 on this side and minus 0.3438 on this side. And now any value of R which is less than this minus 0.3438 will be a rejection case, and any value greater than plus 0.3438 is also rejection. So we can say rejection region here and rejection region here also, and this will be the acceptance region in between. Now check whether 0.446 falls in left hand side, right hand side, or in the middle. So you can see that 0.446 is greater than 0.3438. Therefore, we can say 0.446 is in the rejection region. Now we need to write a clear statement that yes, R is equal to 0.446 falls in the rejection region. There is sufficient evidence to reject HO. And hence we also need to have a contextual explanation there. This means there is positive correlation. So there is sufficient evidence that there is positive correlation between per capita GDP and CO2 emission. Part B. Barbara believes that a non-linear model would be a better fit to the data. She codes the data using the coding m is equal to log x to the base 10 and c equals log y to the base 10 and obtains the model c equals minus 1.82 plus 0.89 m. The product moment correlation coefficient between c and m is found to be 0.882. Explain how this value supports Barbara's belief. Any value of PMCC close to 1 indicates that there is strong positive correlation. In this case, since R is equal to 0.882 is quite close to 1, it supports Barbara's belief that there is positive correlation. So we could say R is equal to 0.882 means its positive correlation as the value is close to 1. And to answer the question, this supports the conclusion Barbara's belief that there is positive correlation. Part C. Show that the relationship between y and x can be written in the form y equals ax to the power of n, where a and n are constants to be found. So let's first write the given expression y equals ax to the power of n and take logarithm on both sides. So log y to the base 10 equals log ax to the power of n. Therefore, log y to the base 10 equals, using the logarithmic rules, is log a to the base 10 plus n log x. On the other side, we have been told that m is equal to log x to the base 10 and c equals log y to the base 10. Also, c equals minus 1.82 plus 0.89 m. Suppose we replace c and m with these logarithmic expressions, we get log y to the base 10 equals minus 1.82 plus 0.89 log x to the base 10. Okay. Comparing this and this, we can see log y to the base 10, yes, log a to the base 10 should be minus 1.82. So we can say, therefore, log a to the base 10 equals minus 1.82. Therefore, a should be equal to, bring the base to the other side and raise this to the index value, minus 1.82. And putting that into the calculator, we get 0.015. So keep it there. Now let's look for the value of n. N log x is equal to this. So n log x is equal to 0.89 log x to the base 10. Okay, this also to the base 10. Therefore, n should be equal to 0.89. So we got both n and a values. The question wants us to write this in the form y equals ax to the power of n. So we can write y equals 0.015 x to the power of 0.89. Question 4. Magali is studying the mean total cloud cover in octas for Liu charts in 1987 using data from the large dataset. The daily mean total cloud cover for all 184 days from the large dataset is summarized in the table below. One of the 184 days is selected at random. Find the probability that it has a daily mean total cloud cover of 6 or greater. A cloud cover of 6 or greater would mean this number of days, right? Therefore, we will add these three and find the ratio of that to 184 days to find the required probability. So that is 52 plus 52 plus 28 over 184 days. That is equal to 132 over 184. That simplifies to 0.717. Part B. Magali is investigating whether the daily mean total cloud cover can be modeled using a binomial distribution. She uses the random variable x to denote the daily mean total cloud cover and believes that x follows binomial 8, 0.76. Using Magali's model, find the probability of x being greater than or equal to 6. So let's write the binomial distribution model here. X follows binomial, n is 8, p is 0.76, and what is the probability of x is greater than or equal to 6. Let's put this into the binomial distribution calculator. N is equal to 8 and pi value, that is the probability, is 0.76, and we want to know equal to and greater than 6. Therefore, I should put here 5, and that comes 0.7033. 0.703 to 3 decimal places. Second part, find to 1 decimal place the expected number of days in a sample of 184 days with a daily mean total cloud cover of 7. Here our strategy should be, we will first use the binomial model to find the probability of the total cloud cover being equal to 7, and we will then multiply that by 184 to get the expected value. So let's write that once again. X follows binomial distribution, 8, 0.76. Okay. What's the probability of x being equal to 7? Going back to the binomial distribution calculator, let's put between 7 and 7. And that gives us 0.2812. 0.2812. The expected value is always probability multiplied by the total number. Therefore, it is 0.2812 times 184. That's equal to 51.7. Part C. Explain whether or not your answers to Part B support the use of Magali's model. From the table, we can see that the actual number of days which had a cloud cover of 7 is 52. And from the model calculation that we had, it was 51.7. So they are quite close to each other. Therefore, we can say this model is supported. So we say yes. Then we give the explanation. The actual reading, the actual number of 52 days for cloud cover of 7 matches with the calculated value, with the model calculated value of 51.7. Hence, it supports the model. Part D. Find the proportion of these days when the daily mean total cloud cover was 6 or greater. Part D. There were 28 days that had a daily mean total cloud cover of 8. For these 28 days, the daily mean total cloud cover for the following day is shown in the table below. Find the proportion of these days when the daily mean total cloud cover was 6 or greater. So we add these three and put it as a ratio of 28. So it is 5 plus 9 plus 9. So it is 5 plus 9 plus 9 out of a total of 28 days. That is equal to 23 over 28, giving 0.821. Part E. Comment on Magali's model in light of your answer to Part D. We had already calculated from Magali's model the probability of x being greater than or equal to 6, being 0.703. Right. Now for the following day, the probability of cloud cover being more than or equal to 6 is 0.821, which means there is a greater probability of higher cloud cover on the following day based on the previous day's cloud cover, which means these values are not independent, they are dependent. But one of the conditions for being suitable for binomial distribution modeling is the probability should be independent. That is, one day's probability should not affect the next day's probability, which is actually not true in this case. Therefore, we can say that binomial distribution model is not suitable for this because we find a dependence on the probability of cloud cover on one day and the subsequent day. We can say, as per Magali's model, probability of x being greater than or equal to 6 is equal to 0.703 from part B I. Okay. Then we can say for the following day, probability of x being greater than or equal to 6 is a greater value of 0.821 from D. Hence, the cloud cover of consecutive days seems to be dependent or not independent. Therefore, it is not suitable for binomial distribution modeling. Question 5. A machine puts liquid into bottles of perfume. The amount of liquid put into each bottle, dml, follows a normal distribution with mean 25 ml. Given that 15% of bottles contain less than 24.63 ml, find two decimal places the value of k such that probability of d is greater than 24.63 but less than k is equal to 0.45. So let's write the available information. D follows normal distribution with mu equal to 25, but we do not know the variance. We have been told that the probability of D being less than 24.63 is equal to 0.15. So we need to figure out the sigma now to proceed further, and therefore let us standardize this, the z scores. Okay, so let D be equal to z, where z is equal to D minus mu over sigma. Okay, and then probability of z being less than 24.63 minus mu, which is 25, over sigma, which we are after now, is equal to 0.15. Putting this into the inverse normal distribution calculator with the probability being 0.15, mean is equal to 0 and standard deviation 1, and we are after below, and that is minus 1.0364. Therefore z is equal to minus 1.0364, and that is equal to 24.63 take away 25 over sigma. So rearranging this, we can solve for sigma. That is minus 1.0364 sigma equals 24.63 minus 25. And therefore sigma equals 24.63 minus 25 all over minus 1.0364. This will give a positive value because the numerator is negative. That gives a sigma value of 0.3570. Hence we can say D follows normal distribution with mu is equal to 25 and variance is equal to 0.3570 square. Now from this we have to find out k such that D is greater than 24.63 but less than k has a probability of 0.45. So if you draw the normal distribution curve here, so the median is, or mu is 25, sigma is 0.3570, and here and here there are two values. This is 24.63 and this is k. Okay, so we have been told that this is 0.15 or 15%, and this between these two values greater than 24.63 and less than k is equal to 0.45. So these values is 0.45. This tells us that probability of x being less than k should be equal to 0.15 add 0.45 is equal to 0.60. Putting this back into the inverse normal distribution calculator, we can put area as 0.60, mean is equal to 25, standard deviation is equal to 0.3570. Cool. Now we want below, right? So let's recalculate this. That gives us a k value of 25.09. Part B. A random sample of 200 bottles is taken. Using a normal approximation, find the probability that fewer than half of these bottles contain between 24.63 ml and k ml. Here n is 200, which is much more than that for a binomial distribution, and the probability is 0.45, which is close to 0.5. Therefore, it's a fit case for doing normal approximation. So using these two, we can write out first the binomial distribution and then convert that into normal distribution approximation. So let's now write B. Okay. N is equal to 200. Probability is equal to 0.45, and therefore D follows binomial distribution with 200 as n, probability as 0.45. We need to approximate this into normal distribution. Therefore, we should write y follows normal distribution, where here the mean will be np and the variance will be np times 1 minus p. Calculate one by one these values. np is the mu, right? That is equal to 200 times 0.45, and that gives us 90. Park it there. Now we need to have the variance is equal to np bracket 1 minus p, that is equal to 90 bracket 1 minus 0.45 equals 90 times 0.55, that gives me 49.5. When we do normal approximation of the binomial distribution, remember there are three things that we need to do. One is calculating the NP, we did that. Next is calculating the variance, we did that. The third thing is the most important one and most common pitfall for students is not doing the continuity correction. So remember, we need to do three things, then you will not forget. You can use the checklist. So the question says fewer than half of 200. So fewer than half of 200 would actually mean less than 100. Okay. That is, we can say x being less than 100, and that should be converted into y being less than 99.5 using the continuity correction concept. Therefore, using y following normal distribution, mu is equal to 90, variance is equal to 49.5. What's the probability of y being less than 99.5? Let's put that into the calculator and find out. So let us write this using standard deviation also, so that we can put it in the calculator. 90 comma square root of 79.5 gives 7.0356. Then you put square here. Now going back to the calculator, mean is equal to 90, standard deviation is equal to 7.0356, and we want y value below 99.5. Okay, let's put 99.5 here, and that probability is 0.9115. Part C. The machine is adjusted so that the standard deviation of the liquid put in the bottles is now 0.16 ml. Following the adjustments, Hannah believes that the mean amount of liquid put in each bottle is less than 25 ml. She takes a random sample of 20 bottles and finds the mean amount of liquid to be 24.94 ml. Test Hannah's belief at 5% level of significance, and you should state your hypothesis clearly. This is the hardest part of hypothesis testing using normal distribution, but don't panic. If you go logically step by step, this will be easy. Let's start listing out all the information that we have got. So first let's write the hypothesis. The null hypothesis is mu is equal to 25. But we are testing whether the mu has changed to less than 25. So the alternative hypothesis is mu less than 25. What else we do now? Sigma is equal to 0.16, n is equal to 20, d bar is equal to 24.94, alpha is equal to 0.05. As d follows normal distribution, so we write mu is equal to 25, but the variance will change. That will be 0.16 square over the sample size of 20. So that is equal to normal distribution mu 25. Now let's put this into calculator and put this as a decimal value here. I get 1.28 times 10 to the power of minus 3. But this is variance, therefore I need to rewrite this showing the standard deviation so that we can put it in the calculator. So taking square root of this, I get 0.0358 and I can put square here. Very good. Let's park this there now. Now let's write the key statement. Assuming the null hypothesis to be true, the probability of d bar being less than 24.94 is equal to, we put this in the normal distribution calculator. So mu is equal to 25 and standard deviation is 0.0358, and we are looking at d being less than 24.94. So let's write 24.94. That gives us a probability of 0.0469. That is equal to 0.0469. Now we write the conclusion statement. So 0.0469 show that this is less than 0.05. Then we write as 0.0469 is less than 0.05. There is sufficient evidence to reject HO. We also need to give a statement in context. So Hannah's belief that the mean is less than 25 ml is supported by evidence. That's it. That's the end of the question paper. Hope you thoroughly enjoyed it and found the walkthrough useful. Thank you very much for being with me during this walkthrough, and we will meet in the next walkthrough. Till then, bye.